Welcome back. In this lecture, we are going to start studying plane wave propagation in Ferrite medium. And as we said before, Ferrite medium will be uh, used when it is saturated by a DC magnetic field biasing. So the question now is, what will be the situation of the plane wave propagation if the direction of propagation is the same as the direction of the biasing DC magnetic field? Another situation is, what will be the situation if the plane wave is propagating transverse to the biasing DC magnetic field. So, assuming that the biasing DC magnetic field is oriented toward positive z direction, so the first case, when the plane wave is propagating in positive z direction. And we will see when the plane wave is propagating in the same direction of the biasing DC magnetic field, the plane wave will introduce rotation in the polarization, and this rotation will be called Faraday rotation. So propagation in direction of biasing DC magnetic field is defined as the propagation with Faraday rotation. On the other hand, if the biasing DC magnetic field is in the direction Z direction, for example, and the plane wave propagating in X direction or in Y direction, so the direction of propagation in this case is normal to the direction of the biasing DC magnetic field, or in other words, this propagation is transverse to the biasing magnetic field. In this case, we will note that the propagation will depend on the direction of propagation, and this is what is called birefringence effect, and we are going to study this birefringence effect. So in this lecture, we are starting with propagation in the direction of bias. So we say that plane wave propagation in ferrite medium, case 1, propagation in direction of biasing or biased DC magnetic field. Assuming that the DC magnetic biasing field in Z direction, such that the biasing magnetic field is H naught, which has an amplitude H naught in Z direction, and according to Maxwell's equation, the relation between the electric and magnetic fields of the incident plane wave would be curl E equals minus J omega, the tensor of the permeability mu multiplied by H. And here the tensor of the permeability, according to the direction of the biasing magnetic field, it would be as follows: mu J kappa 0 minus J kappa mu 0 0 0 mu naught, which is the permeability of a ferrite medium with a DC magnetic biasing in Z direction. On the other hand, curl H, it would be J omega epsilon E, and epsilon here is the permittivity of the ferrite medium, and it is assumed to be a constant value, not a tensor. And assuming that there is no charges inside the ferrite medium, so according to Gauss law, the divergence of the electric flux density, divergence of D, it will be 0. And because there is no magnetic sources, divergence of B is always 0. This is briefly Maxwell's equation. And assuming that the incident electromagnetic wave is plane wave propagating in Z direction, so in this case, the electric field will be assumed to be vector E naught multiplied by the propagation constant in z direction. And as I said, case 1, the propagation is assumed to be in the direction of the biasing magnetic field. So the electric field is E naught. E naught here, it can be E naught in x direction or E naught in y direction, or a combination between x and y directions, but transverse to the direction of propagation. E naught multiplied by e to the power minus j beta z. E to the power minus j beta z is a forward propagating function in z direction. And the magnetic field H of the incident plane wave would be H naught, and it should be noted that this H naught is not the biasing magnetic field. Actually, I have copied it from the textbook of Buzar, but if I have the opportunity to change it, it should be some other symbol. So this H naught here is the RF signal. This H naught here is the biasing magnetic field. So please take care of this. H naught multiplied by e to the power minus j beta z. And according to the properties of plane wave, the plane wave is constant in the transverse plane. Transverse plane in the present case is the xy plane. So at all the xy plane, the electric field and magnetic field are constant values, which means that the derivative with respect to x and the derivative with respect to y equals 0. So we have only the derivative with respect to z, and the derivative with respect to z will correspond to multiplication by minus j beta. Okay? So we are going to simplify these Kerr relations to find out the x component and y component and z component for both the electric field and magnetic field. So in this case, according to Maxwell's equations and according to the definition of the permeability mu, we can find out the x component here is minus the derivative of Ey with respect to z. Minus the derivative with respect to z means that minus j beta is j beta. So j beta Ey in the x direction would equal the x component here. The x component here is minus j omega mu hx plus j kappa hy. I have taken the x component. So here is mu multiplied by h. So the x component is mu multiplied by hx plus j kappa multiplied by hy. In a similar way, the y component, it would be partial ex by partial z, which is equivalent to minus j beta ex. I have replaced partial by partial z by minus j beta. And the y component, on the other hand, is minus j omega minus j kappa hx plus mu hy. Minus j kappa multiplied by hx plus mu multiplied by hy. Finally, the last term, it will depend on partial by partial x plus partial by partial y, and we know that partial by partial x equals partial by partial y equals 0. So 0 in z direction would equal minus j omega mu naught hz, or in other words, hz equals 0. Okay? This is the simplification of this equation. In a similar way, we can simplify the second equation as the beginning minus the derivative of hy by z is j beta hy would equal the x component here, j omega epsilon ex, and the derivative of hx with respect to z would equal the y component, so minus j beta hx equals j omega epsilon ey, and finally the z component 0 equals j omega epsilon ez. So both hz and ez are 0, which is actually the actual case in the transverse electromagnetic plane wave. So Ez and Hz are 0 as expected for transverse electromagnetic plane wave. So at the beginning, we can conclude from these two zeros that the plane wave inside the ferrite medium, when propagating in the same direction of the biasing DC magnetic field, will also be transverse electromagnetic wave. Okay, so this is our first conclusion. On the other hand, if we divided the value of Hy over Ex, it would be Hy over Ex is omega epsilon over beta, which equal minus Hx over Y. So we can define Y as omega epsilon over beta as the wave admittance inside the ferrite medium. Right? Now, it should be noted that we don't know what is the value of the propagation constant beta inside the ferrite medium. So it is required to find out the value of beta, or the value of the propagation constant inside the ferrite medium, when the plane wave is propagating in the direction of the biasing DC magnetic field. Okay? Alright. If we look at these 6 equations, already we have from these 2 equations concluded that the longitudinal component of Ez and Hz are 0. Now we have 4 transverse components, Ex, Ey, Hx, and Hy. Okay? So, from these 2 equations, we can represent Hx and Hy in terms of Ex and Ey, and use this representation in the above equation. So, in this case, these 2 equations would be represented completely in terms of Ex and Ey only. And then, by arranging these 2 equations, we can represent it in terms of Ex only or Ey only. This is our plan. So, as I said, we have the first 2 equations, Ey as a function of Hx and Hy, and Ex as a function of Hx and Xy. We are going to replace Hy by omega epsilon over beta multiplied by Ex. And we are going to replace Hx by minus omega epsilon over beta multiplied by Ey. And we put the equivalent for Hx and Hy here. From this, we can obtain an equation in terms of Ex and Ey only. This is the first equation. Here, for example, we have j beta Ey and minus j omega mu Hx. Hx, it would be replaced by minus omega epsilon over beta Ey. So this is minus j omega mu multiplied by omega epsilon multiplied by minus 2, it would be plus Ey over beta. And then this beta in the denominator, we are going to multiply both sides by beta. So this would be beta squared and so on. So effectively, this equation is this equation by replacing Hx and Hy by their equivalent from Ex and Ey. In a similar way, the other equation would be represented in terms of Ex and Ey like this. Now we have 2 equations in Ex and Ey, which can be represented as a matrix multiplied by Ex, Ey, by vector Ex, Ey, and this matrix would equal 0. Effectively, Ex and Ey couldn't be simultaneously 0. If they are both 0, this means that there is no fields at all. But the question is, if the determinant of this matrix is 0, this would correspond to the eigenvalue of the problem. And this eigenvalue would introduce the value of beta, which satisfies that this matrix multiplied by Ex, Ey would be 0. So we are going to take the matrix represented, the matrix represented by these two equations. So the determinant of this matrix, it would be this element multiplied by this element minus this element multiplied by this element would equal 0, which is actually omega to the power 4 epsilon to the power 2 kappa squared minus beta squared minus omega squared mu epsilon squared would equal 0. This actually is the characteristic equation or the eigenvalue equation for the propagation constant of the plane wave inside the ferrite medium when the plane wave is propagating in the direction of the DC biasing magnetic field. The next step is to solve this characteristic equation or this eigenvalue equation to determine the value of beta or to determine the propagation constant for the plane wave. And because this equation is second order equation, it is expected that we have two different values for beta. So we will find beta plus or beta minus, where beta plus is omega square root mu square root epsilon multiplied by mu plus kappa, while beta minus is omega multiplied by square root epsilon multiplied by mu minus kappa. This means that we have two different propagation constants for different modes inside the ferrite medium, which accept propagating of plane wave inside the ferrite medium in the direction of the biasing magnetic field. So there are two possible propagation constants, beta plus and beta minus, for the plane wave in this case. We are going to study what will be the plane wave for beta plus and what will be the plane wave for beta minus. So for beta plus, if beta is beta plus, it would be omega square root epsilon multiplied by mu plus kappa. This will correspond to what we are going to call y plus. Y plus, it would be omega epsilon over beta plus. And beta plus, as I said, omega square root epsilon mu plus kappa. So omega, it will be eliminated with omega. We have epsilon here in the numerator and the square root epsilon in the denominator, so it would be square root epsilon. So it would be simply y plus is omega epsilon over beta plus equals square root epsilon over mu plus kappa. Okay, this is the characteristic admittance or wave admittance of the ferrite medium for a plane wave propagating with beta plus. Now, by using beta plus in the equation of, in the first equation for the electric field, which we have already obtained, we are going to apply beta plus here and calculate the relation between Ex and Ey. So if we applied beta plus here, this would be omega squared epsilon multiplied by mu plus kappa. And already we have omega squared mu epsilon, so the remaining part, it would be omega squared epsilon kappa, omega squared epsilon kappa. So beta squared minus omega squared mu epsilon, when we are using beta plus, it would be omega squared epsilon kappa multiplied by Ey, while Ex is j omega squared epsilon kappa Ex, and this equation equals 0. This means that the value of Ey equals minus Gex. The value of Ey equals minus Gex. So assuming Ex is E naught, for example, so the total electric field would be E naught in X direction minus J E naught in Y direction. So E naught multiplied by X direction minus J Y direction. And as we said, it is propagating with beta plus in Z direction. So the dependence on Z, it would be E to the power minus J beta plus Z. Effectively, this equation represent a right-hand circular polarized wave. This means that uh, the mode that propagate with beta plus inside the Ferrite medium is a right-hand circular polarization. On the other hand, if we are looking for the magnetic field, the value of Hy is given by Ex multiplied by Y plus, while Hx is minus Ey multiplied by Hx is minus Y plus multiplied by Ey. So in this case, the magnetic field can be represented as E naught multiplied by Y plus multiplied by J in X direction plus Y direction. J in X direction is coming from what? Is coming from Hx is proportional to minus Y plus multiplied by Ey. And Ey is already minus J. So minus J minus minus, it would be plus J in X direction, because here Hx. On the other hand, Hy is proportional to Y plus Ex and X here. So in Y direction, it would be E naught multiplied by Y plus. And the propagation is e to the power minus J beta plus Z. As I said, this plane wave is simply right-hand circular polarization of circular polarized plane wave. This means that the propagation constant beta plus corresponds to a right-hand circular polarization propagating inside the Ferrite medium, and the propagation constant in the same direction of the DC biasing magnetic field. And the wave admittance in this case equals square root epsilon over mu plus kappa. On the other hand, if we are looking for the fields associated with beta minus, in beta minus it would be omega square root epsilon multiplied by mu minus kappa. So in this case, y minus, it would be omega epsilon over beta minus, which will be square root epsilon over mu minus kappa, which is different from the characteristic impedance or characteristic admittance of y plus. This means that the propagation in negative will propagate with different characteristic impedance, will propagate with different propagation constant, and so on. On the other hand, if we apply beta minus in the first equation for the electric field here, we are going to replace beta squared by omega squared epsilon mu minus kappa. So in this case, omega squared mu epsilon will be eliminated with omega squared mu epsilon. The remaining part, it would be minus omega squared epsilon kappa. So the equation in this case, it would be simply this j omega epsilon omega squared epsilon kappa ex minus minus omega squared epsilon kappa ey. So in other words, the value of ey would equal the value of jex, not minus. So in this case, the total electric field for beta minus, we are going to call it E minus, would be E naught in X direction plus J E naught in Y direction, which is actually left-hand circular polarized wave, and it will be propagating with the propagation constant e to the power minus J beta minus Z. Okay? On the other hand, the magnetic field of this electric field, it can be obtained by the relation or by replacing Hy by Y minus Ex, which is E naught, and Hx, it would be replaced by minus Y minus multiplied by Ey, which is also E naught. So in this case, the value of the X component for the H is minus J Ey naught multiplied by Y minus, while the value of the Y component, it would be E naught multiplied by Y minus, and it would be propagating with propagation constant e to the power minus J beta Z. This is actually a left-hand circular polarized plane wave. So beta minus correspond to a left-hand circumpolarized plane wave, and it has a completely different characteristic admittance. So it has completely different propagation constant and completely different characteristic admittance. This means that the right hand and left hand circumpolarized plane waves are the source-free modes of Z-biased ferrite medium. So, or in other words, the eigenvectors or the solution for source-free wave equation. Right-hand circumpolarization and left-hand circumpolarization plane wave propagates through the ferrite medium with different propagation constants. So the right hand is propagating with beta plus, the left hand is propagating with beta minus. This means that the phase shift of the right hand after a certain distance will be completely different from the phase shift of left hand circumpolarization because of the propagation constant is different. Also, the characteristic admittance of the right hand is different from the characteristic impedance of the left hand. It means that inside the ferrite medium, we have a right hand circumpolarization propagating in a certain mode and another left hand circumpolarization propagating in completely different mode. Comments on the two propagation constant. The physical explanation for this effect is that the magnetic bias field creates a preferred direction for the magnetic dipole precision. And one sense of circumpolarization, which is the right hand, cause precision is this preferred direction. So in our case, the right hand circumpolarization in the preferred direction of precision, while the other sense of polarization causes precision in opposite direction. And we have already studied this before when we studied different circumpolarized plane wave or different circumpolarized magnetic fields inside the ferrite medium. For right-hand circumpolarized plane wave, the ferrite material can be represented with an effective permeability mu plus kappa. While for left-hand circumpolarized plane wave, the effective permeability it would be mu minus kappa. This means that if I'm ignoring completely what is ferrite, I'm saying that I have a medium with effective permeability for right-hand circumpolarization, mu r, for example, equal mu plus kappa. And on the other hand, for left-hand circumpolarization, it has completely different permeability, which is equal mu minus kappa. When losses are present, the attenuation constant for right-hand circumpolarization and left-hand circumpolarization will also be different. This means that, once again, the right hand will be propagating with some characteristic, while the left-hand circumpolarization will be propagating with completely different characteristics. Now, according to the analysis in this lecture, we know now the propagation constants inside the ferrite medium in the same direction of the biasing DC magnetic field, it would be beta plus and beta minus for right hand circumpolarization and left hand circumpolarization. And as I said, this is for source free, or if we don't have any source inside the medium. This is the eigenvalues for the medium itself. What will be the situation if I have incident plane wave? And if this incident plane wave is linear polarized, what will be the situation? That's what we are going to see in the next page. Alright? Okay.